So good afternoon. My name is David Howdigi. I'm the Department Head of Civil Engineering at New Mexico State University, also co-chair of this conference. Welcome to this session. Our session is going to be related to unmanned aerial systems for transportation and construction. I want to just give a brief overview of where this particular session came about. This is essentially a spin-off of a session that we had during the 2019 Unmanned Aerial System Technical Analysis and Application Center conference that we had in 2019 here at NMSU. In 2020, it was canceled, but it was the first time that we had the conference in Las Cruces after many years in Santa Fe. And in that particular conference, we had industry representation from FAA, NASA, Department of Energy, Uber, Bell, Department of Defense. And what I felt was missing there was really the transportation organizations on infrastructure related to highway departments and city as far as roadways. And so that's where this came about, and we have 4 exciting presentations that are scheduled for you. The first presentation, I'm going to go ahead and just hit the ground running. Our first presentation comes from Mr. Michael Banasiak. He's the project manager at Collins Engineers, and as you can see here, his presentation focus will be merging drone photogrammetry and underwater multi-beam sonar for scour critical bridges. And so with that, I'll turn it over to Mike.
Okay, thanks, David. Can you hear me?
Yes, I can.
And see my screen?
You're good to go.
Excellent, thank you. So thanks for coming here. Good afternoon. Thanks for joining me. My name is Mike Banasiak. I'm looking forward to sharing with you a topic I find quite interesting, and hopefully you will as well. This presentation is designed to be an hour or more with questions, but I'm fitting it into 15 minutes. So it might seem like we're going fast, but we'll try and touch on a little bit of everything. So the world of structural inspection is changing and evolving, and in a bridge inspection landscape being increasingly shaped by the need for quantitative information and data-driven decisions, we're constantly exploring how new technology can effectively contribute to goals of providing clear data and inspection results to properly influence future decisions and policy. So the looming question and issue, however, is how can we utilize new technology in both efficient and economical manners to add value to existing processes? So that's where this project comes in. So today I'll be sharing results of an idea and project where we combined a few emerging technologies, notably drone photogrammetry, imaging, and surveying, and underwater multi-beam sonar to result in what you'll see are final products that are easy to understand, quantify, and interpret. So we'll go through a case study of some underwater bridge inspections we performed for Montana Department of Transportation in 2019. So they came to us with a handful of their higher priority scour critical bridges. For those of you not familiar with that term, a bridge is defined as scour critical if it meets the criteria of having the foundation of one of the substructure units, so an abutment or a pier, rated as unstable due to observed or evaluated scour, which is essentially the removal of channel bottom material, sand, gravel, rocks, due to swift moving current. So essentially the effects of erosion around substructure units. Oh, we got to mute. Okay. So the intention of this project was that we perform in-depth underwater inspections, including multi-beam imaging, to assess the efficacy of some scour repairs. So riprap, articulated concrete blocks, items placed around a pier to mitigate against the erosive effects of high flow. I'm sorry. So we would use multi-beam imaging, so underwater imaging, to also establish a more detailed baseline for future inspections. These type of underwater inspections is our company's bread and butter. I'm a diver myself, and we use some of these tools to supplement our actual diving inspections. So a little bit about multi-beam sonar. Underwater bridge inspections can be complicated to a variety of factors such as high flow, zero visibility, as evidenced from the photo below the Yellowstone River. And one tool we use to illuminate details of the submerged structures and their adjacent channel bottoms is underwater acoustic imaging. So at its most basic, transducer is mounted to a boat or tripod in the water, shoots sound waves out in all directions, reflecting off surfaces. So be it a pier wall, rocks, timber on the channel bottom, resulting, back to the transducer, resulting in point cloud data, essentially underwater 3D images. This information can be incredibly useful in that not only can it prime the engineer diver with an idea of what to expect and explore underwater, but it also results in hard data that can be replicated in future inspections, compare changing conditions in a more quantitative manner than the subjective perspective of just one diver. This is where UAVs and drones came into play. So underwater bridge inspections aren't simply confined to the waterline and below. There's a lot of valuable information gleaned from embankments, floodplain, the behavior of surrounding terrain that influence the water's effect on substructure units of the bridge, especially in Montana, where water levels of some of these large bridges are highly variable. So Collins engineers, we already use drones in bridge inspections to take aerial channel photos, elevation views, promo videos, but also thought to take it a step further with this particular project by conducting photogrammetry surveying missions at each bridge. And so essentially, photogrammetry from a drone involves flying a drone in a pre-programmed flight pattern where it takes thousands of photos with a given overlap, so typically about 80% ground sample distance, in order to triangulate the ground elevation and form a 3D model in post-processing. Ground control points, GCPs, or marks, typically X's, geo-reference to coordinates, can be used to achieve a higher degree of surveying precision. And while drone-mounted photogrammetry can achieve a degree of accuracy to the fraction of an inch, for this project, and keeping to the notion and goal of deploying technology in its most effective manner, such precision wasn't necessary. For this case, we used a middle range drone equipped with a 4K camera. Surveying in the field amounted to about a 30-minute drone flight, often less. So again, we're pressed for time, so I'm going to dive into some of these examples. So what you will see is basically a 3D navigable image created by merging data from our drone photogrammetry with our underwater multi-beam sonar. So what you see right now is a photo from our drone superimposed on our image, and I'm going to fly through and we're going to talk a little bit about the scour's effect at the bridge. So for this bridge, we are looking upstream. So the water's flowing from south to north, from the bottom of the screen to the top of the screen. You'll notice from our underwater imagery, we capture a little bit of this exposed footing at the upstream nose. And as we zoom out, we notice that the channel is on a little bit of a degree of curvature, resulting in a little bit of an oblique angle of attack at that upstream nose. So a little bit about the model. Red, basically the colored area denotes the waterway. Red is shallow, blues and purples are deeper. So we notice this little area of scour, of local scour in this west span. Potential concerns at this bridge could be migration of the scour to the east, where it might threaten the exposed footing of the pier. So, advantages of this is now, we normally conduct in-water surveying, single beam or multi-beam, acoustic imagery and sonar essentially in the water. So we just typically have a contour map confined to the water. Adding the information from the drone surveying, we now have a a contour map extending into the floodplains outside of the waterway, which can be useful, particularly, doing scour calculations, calculating cross sections, planning for, higher flow events. Again, I'm speeding through this, but I've got some cool examples I'd like to show you. So this is another similar case where you're looking at the drone photo superimposed on our model. And so I'll click and we'll zoom through. So with this example, water is flowing, the river's flowing from the top of the screen to the bottom of the screen. And you'll notice basically we have two piers that are just barely in the water. I want you to pay attention to the riprap along this west embankment. So notice, so we've had some riprap or scour kind of mitigation, scour countermeasures placed along this embankment, basically to kind of encapsulate some of the footing of this pier. Some riprap was placed along this pier, but it looks like it's largely washed away. And from our underwater imaging, we're capturing the side of this exposed spread footing with maybe about a ½ foot remaining embedment. You'll notice that the underwater imagery captures some of the jagged edges of the riprap. And as we zoom out, you can kind of confirm and see the interface, where we capture the riprap via photogrammetry. As we zoom out, you'll understand the obvious reason for some of this local scour is basically, our channel contracts right at the bridge. We have maybe about a 20% contraction of the channel, forcing equivalent flow into a smaller area, resulting in much more turbulence and local scour at the bridge. So I said pay attention to the riprap. So you'll notice right here, basically this riprap that's been placed is starting to undercut. So we've got a big steep cut bank here on the upstream edge, and we're starting to cut into that riprap. And that's captured on our photogrammetry. It would be noted by a normal inspection, but some advantages of this model that we create is that it can be easily replicated, and we can calculate quantities and rates at which potentially this riprap might be, undercut or being washed away. This model we could also calculate quantities of missing riprap for maintenance items to prime contractors for getting better, more accurate bids. And also this model could be given to a contractor to plan their construction and plan their staging at a repair to this bridge that might include further placement of riprap. So I've got about maybe 5 more minutes. I'm gonna go through this example really quick. This is an obvious example of just the visual nature of these models. So we're looking upstream. We've got a large tree trunk lodged at the upstream nose of this bridge. Water's flowing this way. So it's obvious what's happening here. Basically, this tree is diverting flow into this south span. And so we're basically, compromising the hydraulic opening in this bridge just to one span, resulting in some local scour downstream of the bridge and some aggradation as that flow, goes from, moving fast and turbulent to slowed down by that tree where it deposits, the less dense silt and sand. And that's what we saw here. So just a good example of the visual nature of these models and that it doesn't take a bridge engineer or a hydraulic engineer to understand what's going on underwater and what needs to happen with this, which is really the removal of timber debris here. This is my favorite example. I'm going to dive through. So our water is flowing from the bottom of the screen to the top. You'll notice that the substructure units, so the piers and abutments, are built or oriented kind of in a skew compared to where the channel is right now. So we'll zoom through and we'll see the effects of this. So this bridge is situated in a low-lying floodplain, and we're noticing an obvious 180-degree kind of horseshoe bend. So potentially when this bridge was built, maybe 50, 60 years ago, channel was aligned with this substructure unit. But over time, the outer bend of that stream has been, eroded. And now we're looking at about an 80-degree oblique angle of attack, resulting in local scour along that pier. Utility from this kind of drone, this merged model of underwater, and drone imagery, is that we can see clearly the cause and effect. Note these exposed footings of this stream migration. And so over time, if we were to replicate this drone mission, we could measure the rate of migration of this kind of horseshoe bend. We can measure this, the threatening of this approach embankment, and we could better assess use of resources to mitigate this issue, which might consist of some fairly expensive and intrusive processes of trying to reroute the stream with some spur dikes to get it back to more of a straight on orientation with this bridge to mitigate scour. Just going to zoom through this one, and then we'll wrap things up. But this is another one of our larger models. As we zoom through, you'll kind of notice that, above water, we've captured some timber debris. And actually, we've coated the we've color coded the timber debris underwater as pink. And so, with the post processing of these underwater images, just comes back in a point cloud, as opposed to drone photogrammetry where it's photograph based. So the post processing, you're looking at much more of a visual model. Zooming into this pier, this is the most interesting with regard to scour. We notice a big scour depression here. Water is flowing this way. So we notice we've got spread footing exposure. We've got what appears to be undermining or the bottom of the footing exposed. And we've got these concrete articulated blocks that are on the channel bottom placed there to mitigate and scour. But there was no, it seemed that some of these blocks had been washed away out of this scour depression here. So just wanted to call attention to that one. Go through a couple of these underwater images. I'm going to breeze through this because this is about drones. A little bit of future technology. This is some extra underwater scanning that we've been doing. This one's interesting. So this is it's called a bathycopter. It's basically a drone-mounted LiDAR system. So essentially in one, this UAS could fly above both land and water, and by shooting different wavelengths of light, it can survey, perform a topographic survey of both above water and below water. So generating a similar map to what we did in a kind of a merged effort. A drone like this is, $50K and upwards, and but it's pretty slick. The end product it can make without kind of doing it piecemeal like we did. Finally, I think this is just really cool. It's a amphibious drone debuted last year at the Consumer Electronics Show. It's mounted with 4K camera photogrammetry capability, but also underwater multi-beam sonar. So the idea is you could fly a drone surveying mission, land it on the water, and perform in-water sonar, just like what we did. But of course, it's landing on a calm pond, and we're trying to navigate, the Yellowstone River at peak flow. So I have my questions how it would do in some turbulence. But to sum it up, project was a success. We merged two technologies to get what I believe, is significant value added for less for not much extra effort. I'll play out with this. The drone video I took last year of us climbing a bridge inspecting in Wyoming. But to conclude, we use drones for a variety of reasons. And one of my favorites is just taking promo video like this. But we're living in a technological renaissance, and cool new gadgets popping up left and right. While these shiny new toys are fun to play with, imperative to remember that we need to evaluate new technology through a lens of how it can efficiently and economically add value to what what we're already doing. And so the pressure of data-driven decisions, especially in the provisions of asset management world, open opportunities to utilize technology presented today. Basic questions do remain is, how can it cut costs, save time, and gather new or more meaningful data? And so I encourage you moving forward just to analyze new technology with these simple but realistic parameters. So again, thank you very much for your audience. Hope you enjoyed this and learned something as well. Feel free to reach out to me. I'm happy to give private presentations of this full presentation and open up for a lot more Q&A. But with that, David, I'll turn it back to you and we'll get some other presentations here.
Thank you. Thank you, Michael. That was very impressive. And being in the bridge inspection field myself, I could really see where the technology you're using could be quite useful. I mean, is absolutely useful in the day-to-day work that we do. So thank you so much. We're going to go ahead and leave the questions till later so we can get going on the next presentation. I just want to make a quick announcement. Please make sure that your speaker is muted just to make sure that we are appropriate in our comments. And so moving on to the next presentation by Luis Trujillo. If you could go ahead and share your screen, Luis.
All right, can you hear me okay then?
Yes, we can.
All righty, you need video here too? Does that help at all?
Have you shared your screen yet?
Screen is coming up.
Okay. Okay, I could see it.
All right. See if it gets going here. Okay, how's that?
Yep, it's all yours.
All righty. Well, thank you all very much. Appreciate you guys taking the time. So here at Sun Construction, we have 4 different groups here, and I am part of the transportation group. So we mostly are primarily focused on major highway work, large bridge structures, and I also help out the industrial group as well. Pretty much any larger project than just our standard building size, which Sunt was founded on. So any project that's 40 acres or larger. Let's see here. They're down at the bottom there. If you want to grab my email, please do. Please feel free to contact me with any questions, after this presentation. And the other gentlemen's there that helped put all this together here. Let's see here. All right, so this is going to be a list of currently what our group is utilizing UAS technology for. The material inventory, as you can see there, project progress tracking, submittable pay apps, environmental and safety awareness, which, believe it or not, does play a key factor in, I guess, CYAing. You definitely got to cover your butt, and at the same time, you want to protect not just yourself as a pilot, but your company and the environment and your crew. Project and pre-existing survey is definitely key as well there, especially when it comes to your client and commercial and residential private owners. Pre-con material, that can save you tons of money, not just saving you money, but let's say you were to win a project and the material that you were told was on site is not there. That can dramatically affect your your costs and your budget overall. Pre-con and BIM 3D and 4D layout, which is great for the client to see. I have a few pictures on that, so hopefully you guys enjoy that as well. And preventative legal disputes, that is huge, especially before, during, and after the project. Most of them obviously come after, but yeah, I highly recommend having that. And then structural and utility inspections. This is key, especially for for bridge projects. Okay, this particular project here, this is a highway job that we have down in Tucson, Arizona. As you can see here, it is roughly about 3 miles in length and about 1.5 miles wide there. 4 miles in total, as you can see. This project here with the particular unit that we're flying, it is a fixed wing drone. 1.5 hours to fly, 1 LZ to cover this project here. This particular flight, this day, was about 2,600 on the pictures, and processing time. This is in-house processing time, which is about 8 hours. This is on a custom-built unit. It is a desktop, I believe. And we also have a cloud-based processing option that we use as well, and that usually does cut your processing time down by about 1/3, sometimes even less, depending on the size of the job, and of course how many photos you took. This particular project, we had a points to surface RMSE of 0.074. What that is based off of is the point cloud. And excuse me, there's 2 ways that you can do it, or that we do it. You import your point cloud into whatever CAD software you're using, and you create a surface model from that point cloud. Then you take that surface model and you import the ground control points that you utilize to tie down your data. And you compare those two, coordinates from your GCPs to your surface model. You can also use a digital surface model and a digital elevation model. And then again, you're comparing those models to your control point list, or your ground control point list. And that's what we came up with. So those numbers are based off of at the ground control, not in between. And if there's anything that I ask you take away from this, especially if you're focused on tracking the material on and off your site, which is what we mostly get paid off of. When you're tracking 10,000 yards or 5 million yards, and you're getting paid $5 to $7, per yard, that's quite a bit of money that you can either, lose or save yourself, and not just yourself, but your client as well. Because last thing you want to do is you don't want to overbill your client, and at the same time, you don't want to undercut yourself. So it's, you're looking out for both parties there. Let's see here. So this is the same project, just a different view. Again, what you're looking at here is the ortho mosaic image from that flight, not the point cloud. So this is the ortho image. And most of the time what we're utilizing this for, mind you can rotate, pan, scroll, you can do anything and everything you want with the data. You can zoom in, zoom out, and depending on the, the megapixel of your camera, you can get some pretty fine, detail. We also use it to, especially if it's on pre-con, we will utilize this for anything from office setup, trailer setup, where the laydown yards are going to go, truck lineup, equipment lineup, and the biggest thing that we use this for on large projects is how we want the haul route to go. Because as we all know, especially on big projects, your haul route can make or break you sometimes in fuel costs alone, wear and tear on, tires, the equipment, so on and so forth. So these little things can definitely save a lot in the budget over time during the duration of that job. Whether your project's 3 months or 3 years, it really does help. The other thing that it does too for us is if everything, we feel is set up and designed correctly, it also does help us complete the project earlier than expected. So that's always a plus. And again, just another view from it. The other thing too that you utilize this for is, again, and you might hear me say this quite a bit, throughout this presentation, is a pre-existing survey of the job. This picture is quite, it's zoomed out quite a bit, but when you do zoom in, you really do capture a lot of the details, especially to, believe it or not, the driveways in and out of every business up and down, this particular job site. And we have had issues in the past where, whether it's private or commercial, we'll have, an owner contact us saying that, our equipment caused damage to their property, whether it was their driveway, their fence line, their landscaping, whatever it may be. And if you're fortunate enough to be able to fly the job, however you decide, once a week, every 2 weeks, you have proof. You have proof to show that, look, on this date we flew this project, and this is what we captured. It's not showing what you're saying on this date for some reason. Is it by chance? Maybe, you might be mistaken. City truck might have come and done it. I mean, who knows? There could be a number of options. But anyways, this really does save yourself from lawsuits down the line, God forbid. This particular project here, I think this is, give me a second here, sorry. This one here is another highway project in Corsicana, Texas. This is one half of that project, so about 4.7 miles. This one here took a little bit longer to fly, 3 hours to fly, 3 LZs. Reason being here for the 3 LZs was, I believe it was the wind that day. For this particular flight, the winds were roughly about 18 knots. And when the winds do pick up a bit higher, we definitely want to keep that UAS within eyesight of the pick and any visual observers that, we are using for that project, or for that flight, I should say. This one here was roughly 1,800 images and about 17 hours to process here. And this RMS value on this project came in just under 700s. To us, that's great. I have heard many people, their claim to fame is how accurate they're getting on their data. And I've heard people say that they're getting, 100, 200. I've even heard people claim that they're getting in the thousands. And I'm not saying that's not possible. I just rather not, I don't want to lie to you guys, okay? Those numbers, most of the time, are based off of how accurate they clicked on the photo compared to the ground control points. That's not the accuracy of the data itself to the ground control. In a photogrammetry, you're obviously generating a point cloud from a photo, and you're going to get a lot of noise in your photo, especially on homogeneous ground. Homogeneous ground being anything that is very hard, compact, solid material. Obviously concrete, pavement, but believe it or not, even haul roads. If you're on a mine site, those haul roads are extremely compact, which generate reflection, which creates noise. And within that, your point cloud is not going to be completely flat. And utilizing photogrammetry tech, you're going to get noise no matter what. On dirt, from what we've seen, is about the best data that you will ever get. It's the most accurate data you will get. Hence why we utilize it on our jobs to track our material. So keep that in mind, please, especially when it comes to verifying your data. This is that same project. This is the east end of that job here. And this was just before, I shouldn't say just before, but this was before these structures were actually put in. I'm not sure if you guys, I'm not sure if you guys can see my mouse there, but we have a railroad going right here. So we're having an overpass going in, and it's going to connect to this highway here and headed to, I think this was the west on this particular project here, this being the east side, of course. Heading to the west, it was another 12 miles of project there that we had flown. So utilizing this here, we like to utilize the progress tracking, especially on this particular job, for environmental reasons as well. We had to stay within limits of this property here, and this was privately owned land, as well as everything outside of it, both for private, the owner himself, and then for environmental reasons. We didn't want any containers containing any hazardous fluids or anything like that leaking onto the property. It's not a good call for us or the environment, of course. This was the west side of that job. So here we have two sections. I hope you can see my mouse there. Two sections of highway here, an overpass going across this other highway, and then connecting over here, which was going to connect to that other east end of the project there. This particular project was roughly 23 miles in total, three data sets. So for this particular flight, we broke it up into 3 data sets, as you can see there. The reason why we did that is for the file size. File size was astronomical on this particular project. This section here, I believe, well, as you can see, just this section alone was 27,000 feet. So in total, I think we were looking at about 8 miles for this one here. So again, 23 miles in total, 3 days to fly, 8 hours each day, and that depends on the time of the year. Reason why I say that is, as you guys know, in the summertime, we have more daylight. But at the same time, depending on the terrain you're flying, as far as us, we don't like to start flying as soon as the sun comes up, especially on terrain like this. You can't tell here, but I'll show you some more photos in a bit. This terrain was very difficult. It had a lot of slopes. It ranged anywhere from 1,500 feet all the way down to 400 feet. So there were a lot of mountains. Well, when you have that, you have a lot of shadowing. And shadowing technology has gotten better. So you do get data now where there are shadows, but the darker and deeper that shadow is, the less data you will have. So we truly like to fly at ideal times for the day, which ideally is anywhere between 10 and 2. But for this project, we were starting, I believe, right around 9 o'clock in the morning and finishing about 4 o'clock in the afternoon. Summertime, we can get started a little bit earlier and start about 6:30 or 7. Again, depending on your terrain, and finishing at about 6 or 6:30. So you get a lot more flight time there. This particular project, we did not use ground control, and the only reason why is because they only wanted it flown for a pre-existing survey without elevations. They just wanted to see what was there, what has, just get up and an updated ortho image. That's all it pretty much was. And I got to get going here because I'm running out of time. And I don't want to leave you guys with a half presentation. Okay, so again, updated ortho image only. This right here was the northern portion of that project. So at its widest point, this project, as you can see there, was roughly 3,000 feet wide. This is, I don't know if you guys are familiar with Arizona at all, but this was the I-17. This was about, I'd say, almost midway between Flagstaff and Phoenix. That's where this project was. We're going after a current project there, as a matter of fact. This is another section of that there. Here you can see the I-17. You got the frontage roads there. You got, the other road going underneath there. So drone technology really does allow you to capture a lot of data in a short amount of time. Again, it just depends on what you're going to utilize it for. Another section of that project there. All right, our deliverables and what we have. A data quality report. This is key. This is key to proving the accuracy of your data, not just to yourself, but to your client, of course, and in-house. For your own in-house records, I guess you'd say, for lack of a better term there. Your densified and or grid point clouds. So there is a big difference there. On a grid, obviously you can specify how you want that grid. You want a half a foot, 1 foot, 3 foot. But when you do a grid point cloud, what we've noticed is you lose a lot of data. You lose the berms, you just lose too much data. So a densified point cloud, in our opinion, is the way to go. I'm really running out of time. I got about 3 minutes here, so I'm going to run through this. I apologize. 3D mesh, a raster DSM, your raster there as well for your terrain, a complete ortho image, contours starting at 1/10 of a foot all the way up to whatever you prefer, and an updated Google Map image, which a lot of our guys like because they're more familiar with Google Maps. Okay, so this image here, can you guys tell what is the difference? Obviously, it's the same intersection, but one picture is the ortho image and one picture is the point cloud. And what I wanted to show here was how dense your point clouds can actually get and the amount of data that they do capture. So obviously, the top one being your ortho, your bottom being your point cloud. Again, depending on overlap, the camera you're using, so on and so forth, you can literally generate data on an average of every 2 to 3/10 of a foot. That's that's your point density, and that's extremely impressive, as you can see here. Again, the ortho image up top, contours here with your heat map of that same area. Material inventory. So here we also use this to track inventory that we are either paying someone to remove from our project or we are bringing dirt on to that project. Again, you're just looking out for yourself and for your client here or the company that you are paying to remove that material from your job. It's just keeping everybody honest.
Louis, you have about a minute or
Yes.
so to get completed.
Okay, 10-4. Thank you much. Here for, again, we had pipe go in on this project here. The spillage left over there. This is just what we're trying to track there. Swelling and shrinkage, of course, and we paid, to have that material removed from the job there. This one here is for progress tracking. Just utilizing these in-house, just wanting to keep track of the project, where it's going. This project here, or this slide here is showing 2 flights compared to 3 surface models. And again, we utilize this constantly just to, run our quantities and then to see where the project is at its current state. My apologies here. One last thing before I'm up, I know I'm losing here, but one thing I really want you guys to see here, you can literally import the surface models your surveyors are using in the field and take that same exact surface model, I want you to see this one here, and compare that to what is on the ground. So you can run extremely accurate volumetric reports from this. So please utilize that technology. It is impressive. Here as well, we are just doing as-builds, verifying that all of the pipe is going in where it needs to be on the job. David, am I up on time there, sir?
Yeah, if you could just
Can't
kind
hear
of
you.
summarize it. Yeah, so we could make sure that we give enough time to the other 2 presenters.
Absolutely. So pretty much what I'd like to finish with is definitely choose the technology you're going to fly with wisely for the application you are going to use it for. RTK and the PPK tech is imperative for this type of work. Flying large projects, tracking material, please do that. Use that technology. Communication between yourself, your project managers, and in the field. And last but not least, verify your data. please verify the accuracy of your data, not just at the ground control points, but in between your ground control points. That's the data that floats. That's the data can get away from you and can really screw up your numbers. So thank you very much for your time. I appreciate it.
Thank you, Louis. Very impressive. And by the way, I forgot to mention Louis's affiliation. He's a project survey layout manager at Sun Construction. And his information is also on the website. You can, on the TransCon website, you could find his information there. So thank you, Louis. Appreciate it.
Thank you, guys. Appreciate it.
All right, so to move ahead, our next presenter is Dr. Christopher Lippett. Dr. Lippett, if you want to go ahead and share your screen.
All righty, working on that.
Okay, and as he's doing that, I'll go ahead and give him a brief introduction. As you could see here, he's an associate professor at the University of New Mexico, and his topic is remote sensing for infrastructure damage detection. So I'll turn it over to you, Christopher. Go ahead.
Thanks, David. Yeah, so just a little precursor. As David mentioned, I'm a professor, so I'm looking at this from maybe a little bit stepped back. We do a lot of applied work, but this presentation is trying to look at kind of how things are changing and where we're headed for infrastructure inspection in the future. And before I dive in, I'll just mention the Center for the Advancement of Spatial Informatics Research and Education, Aspire at UNM. We operate a lot of aircraft. We teach data science on the imagery from those aircraft. And so any of you who could use a resource in terms of expertise or in terms of data advice, please consider us a resource. So I'm presenting this today with my colleague Su Zhang, who is a civil engineer, but as you see here, I am not a civil engineer. So I apologize in advance if I make any civil engineer faux pas. So what I'd like to talk about today is, as I said, kind of the big picture of where this technology is going. And so you can't really talk about that without talking about kind of big economic trends that are driving a lot of this. And some of that has to do with the hardware that we now all have access to. Some of that has to do with computing, as was implied in the last presentation. There is an amazing amount of computational horsepower brought to a lot of these techniques because we're dealing with very large amounts of data. And in addition to the computing advances, we're working on methods to try to make a lot of this more manageable and more efficient from a user perspective. And so, automation when you're dealing with large quantities of data is really the key, but as I'll try to relay, there's full automation is not here for most applications and is not necessarily the place to start. And so I'll try to make some practical recommendations if you are thinking about spinning up a UAS program at your organization or thinking about hiring it out. So what's driving a lot of this, right? Sensors in general, silicon detectors, thank you guys for buying your cell phones, are through the floor cheap, right? If you look at this graph, it bottoms out. We now have college students that still, were born on this graph, and it's already bottomed out. So you can buy incredible digital sensors for very cheap because we've all been buying so many of them. And the same thing's happening with our platform technologies, right? And so the drones that we now all think of as fairly commonplace and ubiquitous were an impossibility 20 years ago, and were an extremely expensive and time-intensive activity 10 years ago, and now are becoming really routinely available, and as you're seeing, economically practical to apply for a lot of different applications. Certainly not many, and the hype exceeds the reality at the moment, but that will change. And so when we talk about platforms, as a remote sensing scientist, platforms, anything that carries the sensor, right? And so We talk about UAS platforms. These ones on the top here are all UAS2, and there's many, many more, obviously. But it's these ones on the bottom, these kind of low altitude systems that what you see here on the left is actually a Gatewing. It's the precursor to the Trimble X-Wing system. They bought Gatewing, and then swarms of micro drones are becoming a reality. We all saw them at the Olympics, but it's becoming a reality for sensing and practical for sensing in some cases. And then the ones we all know are rotary wings. Those are the ones that we curse at the beach, and everybody's uncle now has crashed at least one of. So this is what it used to take not that long ago. This is 2008, I believe. So this is, we built an airplane over a period of a few months. We wired up a $6,000 flight computer that came off of a missile, and we put a 10-pound, 3 CCD color infrared sensor into this boat. And a year later, we were collecting some data, and a day after that, we promptly crashed it into the ground and destroyed the whole thing. So things have changed, right? I nowadays, you can go and order a drone on Amazon, and without any training at all, you can take it off, collect data on day one, and if you're really lucky, you'll get it back on day one too. And you can do some pretty amazing things with these aircraft at this point. And that trend of how easy that is and the capability of those systems is not going anywhere, right? 5 years ago, having obstacle avoidance and an ability to do some autonomous navigation to avoid obstacles was unheard of. And now it's in all of the consumer drones that you're buying. So when we talk about computational advancements, so we have cheap sensors, cheap platforms. And so, anybody can go. I mean, a Mavic 2 from DJI is carrying a 1-inch GCD Hasselblad 20 megapixel sensor that, most of us don't own a camera of that quality at home. And it's coming on a consumer drone. So the data collection's easy. Computationally, we heard about the cloud, and that's a great resource, unlimited GPU cycles, unlimited CPU cycles, but pushing large quantities of data up into the cloud, as anyone who's tried can tell you, is not necessarily a straightforward thing to do. In fact, it's still often the fastest way to get large quantities of data into AWS or Azure or somewhere else is to ship them a drive by FedEx overnight is faster than uploading it, unless you happen to be at one of our campuses on a T1 line or something else. So the cloud provides a lot of capability, but I would argue is not really going to solve our kind of bulk data processing solutions in the long term. What it is going to solve is the distribution problem. And so what that means is that no one has to have the data on their machine anymore. No one has to have the software on their machine anymore. Once the data have been bulk processed, they are ubiquitously available, ubiquitously queryable by an infinite number of people using, HTML5 web protocols and a simple browser. The other big computational advancement, obviously, is GPUs. And if you don't have NVIDIA stock yet, I suggest you get it because they are enabling all kinds of things, not just Bitcoins. They are the core behind all of the SFM-MVS data that we were just looking at in the last presentation, all of those surface models. If you didn't do those on GPUs, they would be impossible. They would, small blocks are possible over periods of hours, and large blocks are impossible without GPU processing. And so all of that is feeding and making bigger and bigger jobs more and more practical, and means that we can ask the system to do more and more intensive analytics on those big data sets. And I promise I'll get away from text in just a second here. So the last presentation we were looking at, the surface models and the orthomosaics that are pretty readily available to produce in commercial software at this point. There's good competition in that space. There's at least a dozen providers of software. They all run on GPUs, but that wasn't possible 15 years ago because of this tech, both the hardware and these techniques had not been adapted to photogrammetry yet. Those automated bundle block adjustments have a tremendous amount of power, as you saw in the last presentation, and we've done some work on them that you know, the limits have not been hit yet for sure. So I'll talk about that as one of the big techniques underlying a lot of how many of you I think would think about using drones first. Talk about some work we've done in change detection for infrastructure at very high spatial resolution. So at the crack scale, where we're detecting, you know, delaminations and cracks and rutting and shoving and other types of small deformations. And then I'll talk to you about some work we're doing with advanced feature detectors, because these, to me, are the building blocks of inspecting infrastructure from drones. And so let me tell you a little bit why. So this is just a quick summary. This is changing quickly. I'm sure it's out of date by now. It was only put together a few weeks ago, but I'm sure it's out of date already. These things are just now, as we're talking, percolating out. I don't need to tell most people on this call, out into real business operations being relied on. Leaders have been doing it for a number of years already. The middle of the pack is adopting as we speak. And so all of this that I'm saying now will be different, you know, shortly, thanks to all of you folks. So the photogrammetric techniques that were being referenced in the past two presentations are dependent on an approach called structure from motion. When we do traditional photogrammetry, it was a much more manual process. This technique is actually adopted from robotics and from trying to use a camera to reconstruct a scene. SFM-MVS, structure from motion multi-view stereo, is the techniques that you've seen today. SLAM is a related technique that lets you do things much faster. So you may have seen mobile apps for doing 3D pile scanning, or when you are able to put the couch in your living room before you actually purchase it, right? SLAM is using your cell phone camera to reconstruct the surface of the floor and to be able to estimate where it should place that sofa. Right? Well, so those techniques, it turns out, have no limit in terms of their scale. The only limitation is the data that you feed them. So what you're looking at here is from a number of years ago now, back when from Sue's dissertation work, actually. This is a crosswalk on North Campus at UNM, acquired from a helium balloon with a student holding a tether. And this run through an SFM-MVS technique, right? What you're seeing on the left is paint and asphalt and the reflectivity of those surfaces. What you're seeing on the right is the actual surface, and you can see some of that noise that was being referenced, but you can also see that the actual paint lines are resolved in that process. And so that led us to think, well, you know, what are there limits to this? And so far we haven't found them. I have a student right now working on macro invertebrates in waterborne macroinvertebrates. So we're going to push the scales a little bit more soon. But what this is 10 different sites collecting 16 RTK points at each of those sites, 6 of them for calibration, 10 independent points that weren't used as part of the model for validation. And what you can see is those are millimeters. And those are millimeters that are, you know, the RTK error after opus correction was 4 millimeters in the horizontal and 6 millimeters in the vertical. And our RMSEs are 4 millimeters in the horizontal and 6 millimeters in the vertical. So we can't parse the error between the data sets and the RTK. In practice, this is dependent on a whole lot of things, but it is possible to use this at any scale and to think about scanning very fine detailed surfaces. And these same techniques can be used, for example, for imaging from the bumper of a van instead of from a UAV. But if you want to do change detection for this, and so change detection meaning that we're automating the identification of new stuff in the scene or changes in the scene, it becomes really difficult. There's a lot of distortions in imagery, and I won't go into the details of that, but terrain causes massive distortions. And in high resolution scenes, terrain can be something like a curb or the curvature of a road. That all causes distortions. And so if you want to be able to actually compare one image to another, right, then you have to take some special care in how you acquire it. And so this is a technique we call repeat station imaging. I'll just show you a couple of scenes of imagery from that. This is actually up at Camp Roberts in Northern California for a Defense Department demonstration. But what you're looking at here is a couple of scenes of data. And I'm one of those shadow dots running around moving targets. What this project demonstrated was onboard change detection. So we were flying this and we were detecting all of these changes on the fly for the purposes of security applications. And so the technology, if you think about it, is already available to be able to detect really small stuff, right? In this case, we're detecting things on the order of a few inches to feet. In this case, I'll show you another one here. We're detecting the movement of mostly vehicles. But if you've ever tried to work with imagery and line up imagery like this, you've probably never seen imagery line up this well. And that's because of this repeat station imaging approach that we've been using for a number of years. And it makes it so we can completely automate this process. This imagery is co-registered on board. We find the changes on board, and we actually use it like a server in the sky to come in through web protocols to see all those changes. And so you can see what is hard for the naked eye to identify becomes quite straightforward to identify. Well, it turns out this also works quite well in 3D. And so you can, if you use repeat station imaging, meaning that we actually acquire from the exact same photo stations using the exact same sensor, and we process them in a frame by frame way instead of running the orthos first. There's papers here that you can look up, or I can tell you about it in more detail. But if you acquire imagery in that way, we can actually get volumetric change detection to be a lot more accurate as well than we can with a simple DSM to DSM comparison. And
Christopher,
so,
Christopher,
yeah.
This is David. Just to give you a notice here, you got about 3 minutes, okay?
No problem. And so we've been, if you want to think about automating any of that process, then you have to get to something ontological. You have to actually know what you're looking at. And so on that front, this is an example project we're working on with ducks. You can do the same thing to find all the turnbuckles or to find all of a certain feature type. So we're using CNNs, convolutional neural networks, and to identify waterfowl. We fly imagery, we have users label that imagery, and then the CNNs go and identify those objects. These is really now, in that sense, we just teach the machine to go find what we want it to find. And what we have found recently and is that no matter how you implement any of these automated technologies, you've got too much to deal with if you actually want to be able to inspect it. And all of these, the feature detectors, automated change detection, and the automation of elevation extraction and geometric correction are key building blocks to making it so that we can actually leverage these data instead of getting blown away by them and quickly overwhelmed. I'm going to quickly skip over this, but I want to just show you two quick projects. So this is a project doing pipeline inspection, and it's the company that built this was a student of mine, and he is now running a company doing pipeline inspections. It's when you're going to fly thousands of miles of pipeline, finding the anomalies becomes a real task, and that's a lot of human labor. And so we use these feature detectors to actually go and find those. And we could never have looked at the terabytes of data that he's collecting per week, but we can go and find all the things. And then what we quickly figured out is when you're dealing with liability, with infrastructure, and this is another project for the USDOT, having an engineer in the loop can be a really critical part of the process. So we automate parts of the process, and then we bring in the expertise to make it so that we're providing the best answers we can, and a degree of confidence in that result, because it's got that reliable human in the loop that people already trust. So just really quickly, if you are going to think about applying any of this, be intentional about it and get it into your standard operating procedure. Hybridized approaches right now are far more practical than fully automated approaches. So any company that's telling you they can fully automate things, I would be dubious of. Inspection and damage detection is just one use of this type of data. What I find with a lot of people, a lot of users, is that you have to think about all of those uses of as-built and other kind of sides of the company and how they might use those data to justify the initial investment of getting into it. And then the big lesson is just think about the data and what you're going to do with it afterwards. Are you going to store terabytes of data? Are you going to have people analyze and review terabytes of data? Or, and if you are, then what is the workflow and process to make that practical? I'll leave it there.
Dr. Lippitt, thank you so much. Very impressive work that you're doing, quite a bit of applications, and I'm sure people have questions. And as the other presenters, if you could look up the information for the presenters on the TransCon platform, I'm sure they'd love to hear from you. So thanks again, appreciate it. So we have one last presentation in store for all of you. This is a pre-recorded presentation, and it's done by Peter Walper. He's a managing member at Thermalcam USA. And so I'm going to turn that over to Maddie to please play the pre-recorded presentation.
Good afternoon and welcome to the New Mexico 2021 TransCon Conference. I'm Peter Walper with Thermalcam USA, and this afternoon we're going to talk about our drones and solutions for carbon footprint reduction. There we go. I want to cover a couple subjects, visit with you on solar farms, wind farms, and the oil and gas inspections that we do. We're hearing that global energy demand is going to increase by about 28% between 2015 and 40. And we think drones are going to be a solution to this because they bring to the table data accuracy, enhanced efficiency, reduced inspection times, access to sites, and automation of flights. Interesting thing about collecting data with a drone, it's usually 99% accurate, and it can be both historical and repeatable, which is why we use it in these industry segments such as solar, where we do panel inspections, commissioning, and maintenance, and in the wind turbine market where we do blade mapping, and in oil and gas where we look for methane in flares, tanks, pipelines, and locations. We also fly our drones on power lines, inspecting for a quality of transmission and maintenance. It's a good example of a solar farm, and also a good example of what can happen to your panels when you least expect them. The goats on the right. Example on the left is a solar farm in West Texas, and it gives you an indication of how big these farms are. If 1 megawatt takes about 2.5 acres of panels, then us flying a 250 megawatt farm is a pretty big endeavor. We fly about 15 to 20 megawatts per day, or as fast as 30 to 40 megawatts per day, depending on what our scope of work is. Some of the equipment that we're using, looking at an M210 or a 300 drone, a solar meter, and a wind meter. National Renewable Energy Lab identifies 3 major faults. One is a module fault, looking for specific cell damage or diode fails on the panel. Another is a string fault, an example up in the right, might be caused by a frayed cable or something like that. And then a system balance, which is related to module mounting. Looking for essentially four different times when we fly, usually during construction, to identify what's going on in the different phases. We'll do it in a commissioning phase where it's transferred from construction to new owner. We'll fly existing farms, and we'll fly for ongoing maintenance. Flights are staged using KMLs of the site, and then the inspection protocol dictates how high and what the travel is of the drone. The drone will fly on auto mission. It'll capture its data. The data is sent to the software providers and then ultimately to the client. Data collection is pretty extensive. We collect about 1,000 photos, thousands of photos. It's all identifying actionable data. We deliver that to the decision makers in a simple report that identifies numbers and types of defects, the level of damage, the module location, and ultimately we're there to save time, increase safety, and increase efficiency. Thermal capture requires a high resolution camera, usually a 640 by 512. We normally fly with a 13 millimeter lens, and we're trying to provide a visual history of the damages or the defects, what we call the 3Ds, defects, debris, and dung, which is essentially bird food. Our flight height is dictated by what we're trying to capture. If we're looking for individual diodes or cells, we're usually flying at about 120 feet AGL. If we're trying to do a string, we're at 200 feet. And if we're mapping, we're 3 to a max of 400 feet AGL. We'll fly trying to capture an 80-20 overlap. An example of some of the thermal anomalies that we find. One on the left, the blue with all the white dots, is bird poop. The one on the right, in the top right, is a string out of commission, and some on the bottom are individual cells or multi-cells. The irradiance meter can provide solar levels on the panels to give us an indication of when to fly and when not to fly. Beyond visual line of sight is a kind of common buzzword right now, BVLOS. It can speed up the flight and data collection by as much as 50%. It's pretty much limited by how much battery power do we have left. The result is 2-week flight can become 3 days. Means we can increase the efficiency of the flight or the frequency of the flight. We can find more anomalies faster, and we can deliver that back to the farm owner, and he can optimize his production. Solar industry grew by about 50% last year. We think it's going to grow again in 2021. We're thinking, according to Wood Mackenzie, that over the next 10 years, we're going to see about 324 gigawatts of new capacity, which could mean carbon reductions of about 110 million annually. Here's a good example of what we fly or when we fly out in the wind turbine market. You can see all the turbines in the background, and a good example of what the vegetation looks in good old West Texas. Drones will reduce turbine downtime and man hours by about 75%. They are more
Maddie, don't have the sound at this point. I'm not sure if this is across the board or not.
10, also an M300 DJIs. We fly an autonomous drone inspection. It lowers our flight time on a blade to somewhere around 8 to 12 minutes. The software we use increases the accuracy to find 90% of the defects. We can deliver a report to engineering and essentially speak their language with the report. The drone itself carries an RGB camera and a LiDAR system. The RGB documents all the defects. The LiDAR keeps it at about 3 meters from the blade, and the LiDAR also indicates the size of the damage. Plan the mission the same way or similar to what we do in solar farms. We get the information from the client, plan the mission. Mission itself is automated, and then the onboard controller actually dictates the flight path, and the camera system takes all the high-res photos. And then we'll take that data and upload it to the cloud for further processing and deliver it to the client. According to statistics, the year of 2017, there were about 345,000 turbines worldwide, which means about 1 million blades were subject to wear and tear and needed inspection. We think that proper maintenance can increase the annual production of energy by about 5% and bring about 20% profits to the bottom line while extending the life of the turbine. Navigant Research says that the global wind turbine inspection market could grow to about $6 billion in 2024. Delamination cause failure and affect the efficiency of the blade. This is usually caused by environmental damage while in operation, from lightning strikes, hail, or whatever is happening. It can affect both the outside and the inside of the blade. An average blade is about 61 meters in length. 2/3 down that blade, the interior of the blade is about 3 meters high and about 1/2 meter thick. It means that it has limited manned inspection on the final 45 meters. However, blade crawlers, robotic crawlers, can be a solution, and internal drones are gaining more and more popularity. Here's some good pictures of a drone actually in the middle of a blade, and on the right you can see an operator in the nacelle flying the drone. The caged UAVs bring safety to the market faster, they're safer, there's less risk, they shorten inspection time, and they reduce costs. However, they do have some limitations. They have to carry navigation cameras, light systems, positioning, both global and indoor. They're small, they're about 10 centimeters, so they can get to the end of the blade to the record and collect data, which means they have limited time and limited battery capacity. However, the blade manufacturers are recognizing the fact that you can inspect a blade, internal blade inspection with a drone, and they are modifying their construction technology accordingly. Here's a good example of robotics inspecting the outside of the blade. Those robots are compact, they're portable, they can be controlled remotely, they can inspect, they can document, and they can even repair, which is cheaper, faster, and safer than Heister and rope crews. A good example of a robot is the Neuronus robot, which can do a conductivity test on a blade. It can do leading edge protection and repair. It can clean the tower, do a visual inspection, and then it actually can clean the drain hole. A third market is the oil and gas market. See what we look like out in West Texas.
Maddie, please unmute yourself. I think that's what's controlling the voice.
X600 drone with an RGB Sony camera, a TD loss parts per million laser, and an ICI Mirage optical gas camera. You see our drone taking off on the video in the right. flying over some towers. And what we're seeing on the screen on the OGI methane. When we're flying methane, we have to be precise in GPS coordinates. We have to get accurate wind measurements. We have to fly in favorable wind conditions. We need an appropriate flight pattern and a steady flight height. We are, though, superior over helicopter and plane, both of which are expensive, can't do repeatable flights, and give a less accurate analysis of the data. Here's some good photos of the gas camera picking up some leakage in some tanks. This is an interesting slide. This is the tunable diode laser. And you can see how Zach has mapped out on the red line the pipeline that we're going to fly. The yellow and red balloons are parts per million of when the laser has detected on certain footage a leak or evidence of methane. The red ones obviously are the higher parts per million. We can set the levels on the meter accordingly. We're also flying flare stacks. Flare stacks contribute a lot to the methane emissions. We fly them to inspect the structure, the ladders, the platforms, and heat shielding. And we're looking for corrosion or missing objects or mechanical damage, that sort of thing. What we find usually can decide whether this can be helped by regular maintenance or we need to shut down and make a repair. So that's what we think we can bring to the table with drone solutions to reduce the carbon footprint, both in the solar, wind, and oil and gas markets. We're excited about the data accuracy, the enhanced efficiency, and the reduced inspection time, and the exact access to the sites and the automation of flight that the drone can provide. If you have any questions, here's my information. You can reach me at 432-967-4212 or my email address, info@thermalcamusa. Thanks for listening and thanks for attending.